My name is Maggie Hong. I am the EC Robotics Lead.
And I'm Alex O, the Robotics Sub-Team Lead.
And we are BANSHEE UAV, or Battery as Integrated Structures High Endurance Experimental UAV Robotics.
One major issue with commercial UAVs, such as the one seen in Figure 2.1, is limited flight duration. These UAVs can only fly for about an hour before they need to land and refuel. And this becomes an increasingly bigger problem in military applications where these drones are used to scout out the battlefield and collect critical life-saving information. Additionally, if the motors need to fly faster, consuming more electrical power consumption, or if we need to add any additional sensors increasing the weight, this flight duration drastically decreases. To enable long-endurance flight missions, here at BANSHEE UAV, we have developed a replicable robotics ground system for battery replacement, reliable data transfer, and to be operated in off-the-grid locations.
So this is our design of the robotic ground system. It is comprised of three main parts, the first being the ground control station, which is the landing pad for the drone, the battery vending machine, which is a storage system for our LiPo batteries on standby, and the battery transfer pod, which is the robotic arm that grabs the battery from one station to the other. How it works is that the drone will land autonomously onto our station for the robotic arm to grab, bring it to the battery vending machine to be placed into an empty chamber. There, the battery vending machine rotates accordingly, dispenses a new fully charged battery for the robotic arm to grab, bring it back to the drone to be placed inside the drone's chamber, and the drone is ready to take off with a newly fully charged battery. We estimate this turnaround time to be under 3 minutes, which is more optimal than waiting 2 to 4 hours for one singular LiPo battery to charge at once.
So this is our hypothetical long-endurance flight mission, where our UAV will start in Los Angeles and traverse its way all the way to New York. A normal UAV is not able to make this mission because it needs to refuel, so we have installed our UAV pit stops along the way so it can land and then swap out the battery within 3 minutes and get back up and running. If you have looked at other battery swapping research papers, you may have noticed that they only support one type of UAV. However, our system is modular in nature, so we can support currently 3 UAVs. A Stormford quadcopter, the Baby Shark commercial eVTOL UAV provided to us by the Air Force Research Lab, and the Cinch Drone eVTOL UAV, which was a student-designed UAV here at CPP. So, since our system is modular, as long as it's adapted into our system, we can support any UAV.
So the first component of our robotic ground system is the ground control station. It is a large 9x9 AR marker that the drone's computer vision scans and then autonomously onto. Upon landing, the induction coil on the drone will wirelessly connect with the induction coil on the ground station, indicating that the drone is present on the station. The induction coil plays a very critical role as it allows 20 watts of power to be transferred from the ground station to the drone's onboarding electronics. Why is this important? It is important because JSON mission data files are being sent from the drone to the ground station during this whole battery swapping process. Without the onboarding electronics to be kept on, all of that mission data will be erased since it is a volatile system.
Additionally, when the induction coils meet, another process is initiated, the locking mechanism. The locking mechanism is comprised of linear actuators, which can be seen in Figure 8.1 inside its housing. And in Figure 8.2, you can see the locking mechanism in action, where the induction coils connect, activating an interrupt in our system, engaging the linear actuators, holding the drone into place so the battery transfer pod can safely and reliably swap the battery. This is all controlled using our custom-built motor driver PCB, seen in Figure 8.3, which uses a motor controller, a motor driver, and 4 5-volt relays to control the whole system.
So the second component of our robotic ground system is the battery vending machine. It is a circular rotating system shown in Figures 9.1 that uses a NEMA 23-stepper motor to rotate the 8 battery chambers to a specific location. Each battery chamber will have copper contacts to enable seamless disconnect and connecting from the battery to the battery chamber. Housed in the back of the chamber will be multiple electronic circuits, one such as the battery management circuit, which will capture the voltages of the LiPo battery and send it wirelessly to our web app. We have our LiPo charging circuit, which balance charges all the batteries on our battery chamber to a specific percentage, and we also have the locking circuit, which uses solenoids to lock our chambers into place.
The third component of our system is the battery transfer pod, which can be seen right in front of you. It's comprised of many different elements, such as the depth sensing camera, which uses computer vision to detect air echo markers on the battery and determine the relative distance between the battery transfer pod and the battery chamber. This is then sent to our Open Manipulator X, which is a 4-degree of freedom open source robotic arm provided to us by roboticists, which uses inverse kinematic Python scripts in tandem with the distance gathered from the depth sensing camera in order to calculate the angles it needs to move into grab the battery chamber on the fly in any circumstance. Additionally, there's an induction coil, which acts as a custom-built wireless charger for our onboard LiPo battery. We use this LiPo battery so that the pod can traverse along the track without any wires entangling. Here's some real-life footage of our integration. So in figure 11.1 and 11.2, you can see the battery transfer pod integrating with the ground control station and the BBM. And in figure 11.3, you can see the full integration cycle where the drone lands and the battery is swapped with the new one from the battery vending machine. As you can see, all three of our systems work seamlessly together, providing a safe, reliable, and consistent battery swapping process.
Here is the time breakdown of every single motion of our system that you saw previously in the last slide. We are currently trying to improve our system to be faster, since right now the total time it takes for the full integration is 2.5 minutes, which is fairly fast compared to the 2 to 4 hour wait time of a LiPo battery charging.
Our system also provides a user-friendly web application that can be accessed by users globally. So from BANSHEE UAV members to guests, they can log into our secure dashboard and see the robotic ground systems data, such as the flight mission data collected by the ground control station, the battery chamber voltages from the battery vending machine, and a live stream footage from our depth sensing camera on board the battery transfer pod. Please feel free to go to this website when you have time and check out the website.
So now that you've seen our system, how do we power it? Our system should be operated in off-the-grid locations, such as the desert, where we just can't take all our cables and plug it into the outlet like we would do in the lab. Our solution is to provide three 190-watt solar panels that provide up to 540 watts of power. During the times when there is no sun, like a cloudy day, we do have a 48-volt LiPo battery on standby for our system. We are using high current and high voltage, so to protect our system from over-voltage or short-circuiting, we do use DIN rails to protect it, as well as buck converters to distribute the power evenly to all the subsystems. So through this presentation, you have seen what BANSHEE as a whole does and what the prototype that we made can use to be improving the endurance time of UAV drones. Again, the turnover time of our system is under 3 minutes, specifically 2.5 minutes, which is a lot better than having to wait 2 to 4 hours for one single LiPo battery to charge. The application of our work is that our system is autonomous. No humans are interfacing with the system, no humans are controlling the system. So we reduce a lot of human risk and a lot of human interface. Our system is eco-friendly. We do use solar power and PLA, which makes our system very low cost. Our whole system, if you can guess, takes under $2,000 to produce this large prototype. So if we want to produce it all around the United States, as described earlier, we can do so very easily. We would like to thank all our advisors and our sponsors for making BANSHEE what BANSHEE is right now. Thank you.
Questions from the jurors?
What was the time frame? How long did it take to put this together?
Yeah, so this semester we worked on integration of all the parts. Since we described all 3 parts, that took around a year to produce, print out everything, and design. So a year and then 1 semester to fully integrate everything. There were a lot of issues during integration. Yeah, a lot of issues. So I guess that you could say a year and a half.
What is it mostly composed of, material-wise?
I would say almost all of it is PLA.
3D printed?
Yeah, 3D printed. There's some parts that we have to custom order, like the linear actuators, the motors, the robotic arm, the electrical components. But almost all the structure is PLA. There's some wood elements, but yeah, for the most part, it's like 95% PLA.
If you were to, for actual, production of this, would you continue with the material being PLA and 3D printed, or what would you think?
No, so the problem with PLA is that it's not very weather resistant. So under high heat or actually like intensive use over time, it degrades very fast. So if we were to actually produce this, we would probably think of using more of if we were going to do it out of plastic, we would use a more weather resistant material like maybe PETG or ABS. However, I think for this system to be robust and fully autonomous, the best approach would be to manufacture it mostly out of metal. So we would need to simplify the design so that the CNC process or whatever metal manufacturing process we were using could be a lot easier. Because right now it uses some kind of complex structures, so it's not ideal for metal manufacturing at this moment.
What are your guys' next steps?
Yeah, perfect. The next step we want to do is to manufacture and put it to CNC. So we're currently in the process in contact with USC's. They have like a manufacturing lab where you can CNC these materials. And the next step next year is to manufacture or maybe redesign some parts so that it can be more optimal during the process in metal.
Yeah, additionally, at least for the battery transfer pod, this semester we came up with a new design using aluminum extrusions and timing belts in order to kind of simplify the process, or like make it more weather resistant and have it be more manufacturer friendly.
How hard would it be to upgrade the system to support additional types of UAVs?
Yeah, I would say it's very easy for us because all of our components are modular. If you look at this battery chamber on here, that's not at all attached to the drone, so we would just need to make some minor attachment to it. So it would be like adding, if you had like different phone chargers, you just need to make like a male and female connector and then just plug it in.
Yeah. Our system, that chamber is used to be attached to any drone, if possible. And then, since we have the camera onto a robotic arm, it's easy to find where you want to locate and grab.
This is a really, really cool capstone project, right?
Yeah.
It's a research /
Okay, I was gonna ask, can you reiterate what your experimental design and process was and where your methods are?
Yeah, so first we got approached by Lockheed Martin and by the Air Force Research Lab to find a way to fly these drones a lot further, have a longer endurance time. So you can think of it as Tesla. Any EV drivers here? No? Okay. So when you go to like a Tesla charger, you have to wait 45 minutes. And so why not just battery replace that? So that's kind of our pitch to them, and we've been working we started the design of the system using wood and a lot of other 3D material, but our system in the first place was not modular. So we didn't have any way to, let's say if we wanted to add more batteries, or if we wanted to store like more drones, add more drones to our system, we couldn't do that. So we designed we improved the design to a way that it can be modular, since most research, like MIT has the research and IEEE, they don't have modular system. They only can support the Storm 4, which is not very ideal because there's so many drones out there. So we started redesigning our system last year and printing everything with all the circuitries that goes inside our system. And now we're at a point of integration and trying to complete the system to be working and manufacturing it.
I think you misunderstood my question. I understand it's like a problem you're solving. I'm just curious, like, what's your research methodology and like what is your business? So do you have any data collection? I saw you had like times instead of averages that you had recorded.
No. So those times were
How
like,
do you measure success?
yeah. So these times are the times of like, we literally started our system and we timed it every movement. So the movement of the robotic arm grabbing it is one motion. The movement of it traversing across the track is one motion. It's a lot faster on the video because we timed it up.
Yeah, so to actually collect
Yeah.
these times, we run the
Alright,
system
thank you so
over.
much, that is time.